If you haven't done so already, you may pick up your graded quiz over there, and you may turn in your homework for this week. In a few minutes, I'll gather up the homeworks. This will be the last call for homework to turn in. Many of you did well on your quizzes, some of you did not. If you scored under 15 points on your quiz, that would be an indicator that something is not going right, okay? Please seek help. Come visit me during office hours or ask questions or something of that nature now, because after the midterm, I don't want to say it's too late, but as time goes on, it's going to become more and more difficult to catch up or turn things around. Okay, so it's the fourth week of class right now, so we're only 1/3 of the way through our course. If you work hard, things can look up. However, the midterm exam accounts for 30% of your grade. Okay, between the midterm and the final exam, those two exams account for 65% of your grade. So they are worth a lot. Okay, so next week we have a quiz, and then the week after that will be our midterm. So yes.
So we have a quiz, and then the midterm next week right after?
Yes.
So like back to back?
You have 7 days in between a week, from week to week. Okay? So I would not say back to back, but you do have 7 days. I mean, you've known about the dates of our exams from the first day of class. Okay,
yeah, so quick,
Okay, it's the quarter system, so it goes quickly. Okay, I spoke to another person who's taking a class at Mission College, and they meet 4 times a week, 3 hours a day. They finish the entire stats course in 1 month, so it's a high intensity course over there. This is still intense, not as intense as that one. So okay, so anyway, yes.
For the next quizzes, like consecutively, are they all gonna have the chapters from before in it each time, or is it is it just for the chapters that we're learning now?
So next week's quiz will be on chapters 4 and 5. Okay, the midterm will be on chapters 1 through 6. So the quiz you have that has been returned to you covered chapters 1, 2, and 3. Next week's quiz will cover chapters 4 and 5. The midterm will cover chapters 1 through 6. Okay, so next week's quiz is not cumulative, if that was your question. So anyway, some of you are doing well. If you scored, I would say 25 or up, you're probably in fairly good shape. Okay, if you score 20 to 25, there's things you can work on and improve. Under 20, I'd be a little, maybe a little more concerned, and then under 15 or 15 and under, I'd say signifies issues. Okay, so some of your classmates are doing well, so if you're not embarrassed, you can look around you, see who did well, and maybe find somebody to study with that way. All right. Okay. Any questions?
Are you going to go over the answers of the quiz?
I'm not, but is there a particular question you have an issue with?
Yeah, the box plot one.
The box plot. Okay, if you're asking about, depending on which version of your quiz, the minimum or the maximum is either 20 or 100, as signified by the outlier. Okay, the outlier is part of the data, and that does count as part of your minimum or maximum. The IQR and the median and Q1 and Q3 are pretty self-explanatory from the box plot if you study the definition of a box plot. Okay, those 3 lines indicate Q1, the median, and Q3. And that's what you need to know from a box plot. You don't need to know how to draw a box plot yourself from data. but given a box plot, you need to be able to extract that information, which you have to do here. Okay. Yes.
Midterm is gonna be similar question to the quizzes.
You know, I write the quizzes, I write the midterm. They're all coming from my brain, so in my opinion, they're similar. Okay, of course, they're not exactly the same. The big difference is that a lot of the questions on the midterm will be multiple choice. Okay, so there it goes both ways, right? It goes both ways. If you're not unsure about an answer, you can look at the answer choices, and that might give you clues about how to solve it. But there's also the problem where you think you know what you're doing, and you go through the steps, and you can't find your answer matching one of the answer choices. So that would probably indicate that maybe there was an error in your work.
I'm sorry if I missed that, but so the midterm is going to be multiple choice?
There's going to be a multiple choice component and a free open answer component. Yes?
Should we bring Scantrons for the midterm?
I will provide the Scantrons for you. Okay? We'll discuss more of the midterm next week as appropriate. Okay. If there's no other issues, we'll carry on here. And move on to chapter 5. Chapter 5 is our covers probability. This chapter looks a lot more math-like. There's a lot more letters and symbols and multiplication and division and all of that stuff compared to some of the other chapters. Generally, it is students' least favorite chapter. Okay? I mean, some students like it, but I would say overall, this is probably the least favorite chapter that students face in this class. That said, it is important that we learn probability. Okay.
It's my least favorite.
It is your least favorite also? Okay.
I did part of it yesterday.
It's important because it serves as a baseline against which we can compare our data. Okay, so in the future, we will be doing inference. Inference is trying to draw conclusions from our data. And the basic premise of inference is, as we go through life, things are always a little bit different from one another. Okay? Some of the differences that we experience are just due to random chance. Other times, the differences we experience are because there are real systematic causes or effects or things going on. How can we tell the difference between what is actually happening versus what happens from random chance? Okay. Probability allows us to understand what could happen by random chance. Okay. In the future, we'll learn about the data and comparing what the data looks like to what could happen from random chance. Does that make sense, kind of? Okay, so we'll worry about that when that comes, but today we're learning about probability and what things look like due to random chance. Okay, so. said, summed up in a couple sentences. You can write that down in your notes. Yes?
Why does it some other effect exist instead of some other cause exists?
We can put in the word cause here. Some other cause, some other effect, something going on that changes our data. Okay, so the idea is we just want to be able to understand what can happen from random chance alone first, and then we can decide if there's something about our data that makes us believe it might not have occurred from random chance alone. Slide this up. So first, let's talk about randomness. Okay. What does random mean? Random describes something that might be unpredictable. Okay. It's unpredictable to a degree. Okay. So, for example, the outcome of a coin flip can be considered random. And while the outcome of a single coin flip is unpredictable, okay, so the outcome of a single coin flip is unpredictable, we can still understand the nature of coin flips. We understand, we do know that if we flipped a coin many, many times, we should see approximately the same number of heads as we do tails. So, individual coin flips, unpredictable. But coin flips as a whole, we can understand the nature of them. There is the notion of theoretic probability and empirical probability. Sorry. empirical is gonna appear on the SATs now. I don't know if you guys had to take your SATs or not. Does anyone know what empirical means?
It's usually like, isn't it more, it has more evidence to it?
Yeah, empirical means based on evidence, okay? Based on evidence. So, theoretic is based on theory, empirical based on evidence. Okay, so theoretic probability, this is kind of like saying, what is the probability okay, so I'll just, theoretic probability says the probability is based on theory, okay? Okay, and I'm going to write so the probability that a coin lands heads, is this okay, this notation? PR parentheses coin lands heads. This is the probability that a coin lands heads. Theoretic, what is the theoretic probability that a coin lands heads? 50%, okay? I'm going to write 0.5. So that says if I flip a coin, the probability that it's going to land heads is 50%. Right? Empirical probability, on the other hand, probability is based on evidence. In an empirical probability, the probability is based on evidence. So here, we don't know if we are basing ourselves on empirical probability alone, we don't know the probability that a coin will land heads until we flip a coin. And if I flip a coin once and it lands tails, okay? So after one coin flip, I get tails. My empirical probability that a coin lands heads is equal to what? 0. Okay, 0 out of 1. If I flip the coin once and it landed tails, my empirical probability that the coin lands heads so far is 0. If I flip the coin 1,000 times, let's say I've observed 478 heads and 522 tails. Okay, my empirical probability of the coin landing heads is going to be what? 478 divided by, how many times have I flipped the coin? 1,000. My empirical probability is 0.478. So empirical probability, if we have a lot of time, or if we can simulate coin flips or something, we can get empirical probabilities for a lot of things without having to do calculations of any kind. On the other hand, the theoretic probability is based off of what we call rules or axioms of probability. Okay, so there's some math rules that we're going to cover later today that you're going to have to learn about calculating theoretic probabilities. I started off with a coin landing heads because I think we all have an intuitive notion that the probability of a coin landing heads is 50%. Okay? But if you have never seen a coin before in your life, if you are an alien from another galaxy, somehow you've ended up here, somebody talks about the probability that a coin lands heads, you have no understanding of how these things work, you could get the empirical probability just by flipping a coin many, many, many times. And you might do it 1,000 times and you might get 0.478. Okay? This is not exactly the same as the theoretic probability, but it's pretty close. Okay? After one coin flip, it will probably not be very close. Even after 10 coin flips, it probably won't be very close. You've got to do many, many coin flips, and it will get closer. Okay? This is what we call the rule, or the law of large numbers. The law of large numbers says that if we do things many, many, many times, the empirical probability of what we observe should be close to the theoretic probability. Is anything where the outcome is random. Whether it's a coin flip, rolling a die, drawing a card out of a deck, whatever it might be, if we do a random experiment many, many times, the empirical probability, that is the relative frequency based on our observations, should be close to the theoretic probability. I mean, that's a loose definition. The formal definition is a little more complicated, but this is, I think, good enough. Is everything so far okay?
Yeah.
All right, great. I like that. Okay, sometimes theoretic probabilities are difficult to calculate. We're going to learn some of the math rules to find theoretic probabilities. But sometimes the theoretic probabilities, even after learning the math rules and things like that, sometimes the theoretic probabilities are just very, very difficult to calculate. So what do? Well, sometimes we might not be able to calculate the theoretic probability directly using our mathematical rules. But sometimes we can do a simulation of the random experiment. Okay? We can simulate things using a computer program, whatever it might be. And so, if we can simulate the random event, or the random experiment, we can simulate it many, many, many times and get a simulated empirical probability. our simulation is good, this simulated empirical probability should be close to the true probability, or the theoretic probability. So sometimes this is done. Can you guys think of any scenario where we run simulations to get an empirical probability or simulated probability? Yeah?
And then maybe like city plan, like civil engineering with like traffic lights and
Okay,
intersections.
okay, that's one. Yeah, sometimes we run simulations there. You know, recently, so we just had the World Cup. Okay, a lot of times, you know, before the match, they'll say, you know, Germany is favored to win or Argentina is favored to win, and they'll say the probability that this team will win is, you know, 57%. How did they get that 57%? They've done simulations. Okay, so if you ever have video games, okay, sometimes you can just have the computer play against the computer, and depending on how good this simulation is, you can see a match played out, and one of the teams will win. Okay, and if you had a lot of time, you could run that same simulated match over and over and over again. And sometimes one team, you know, the first team will win, and sometimes the second team will win. Okay, and let's say you had a lot of time, or a bunch of computers, or a bunch of different things to run a bunch of these simulations. You could have them play out maybe 1,000 simulated matches or 10,000 simulated matches, and maybe in 55% of those games, Germany wins, and maybe in 45% of those games, Argentina wins. And a lot of times, sports websites will do some kind of analysis like that to give you a percentage of the team winning. Okay. Because is there a mathematical formula for figuring out which team is going to win? Not a very good one, okay? If there is one, it's probably not very good. So right now, in terms of predicting teams that will win a sports match or sports competition, simulation might be the best tool that we have. Okay. All right. And so we're not going to learn how to run simulations of sports matches, but we can learn simulations of very simple just a very simple simulation. Very simple simulation using random numbers. Okay? Random numbers or random digits is basically you ask, give me a random digit, and a computer or a book or whatever it might be, you're going to get back the digits either 0, 1, 2, 3. Okay? 0 through 9, and each of these digits show up with equal probability. We cannot predict what digit will show up next. However, if we looked at many, 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 many digits, overall, we should see about the same number of 7s as we see the number of 4s versus the numbers 2 or 8 or whatever. All of these digits should show up at about equal, with equal probability, okay, after many, many tries. But of course, if we just looked at 20 digits or even 100 digits, it probably won't all show up in exactly the same proportion. So with that in mind, can we use these random numbers to simulate a coin flip? Okay. Well, a coin flip has two outcomes, heads or tails. And these two outcomes have equal probability. So we just have to, what we might call, map some of these digits to heads and some of the digits to tails so that heads and tails have equal probability of showing up in our simulation. Okay? So one way to do this is a wasteful way, but one way is to just assign one of the digits to heads and one of the digits to tails. And what do we do with the rest of the digits? We just throw them away. Okay? That's a wasteful way. But if we just say every time you see a 0, that means we got heads, and every time you see a 1, that means we got tails, and everything else just ignore, that would simulate heads and tails of equal probability, because we expect to see in the long run about the same number of zeros as we do in number ones. Okay? But again, we're wasting a bunch of digits. So a better way would be to assign 5 of the digits to heads and 5 of the digits to tails. Again, each of these digits show up with equal probability. So if 5 digits are assigned to heads and 5 digits are assigned to tails, we would still expect heads and tails to show up with equal probability. And however you want to choose your 5 digits, whether it's even digits to heads and odd digits to tails, or digits 0 through 4 to heads and 5 through 9 to tails, or however you want to do it, as long as you're assigning the same number of digits to heads as you are to tails, you can simulate a coin flip this way. Is that okay? Does that make sense? Anybody confused? Okay, so the outcomes. Sorry, I know you guys are writing. I'm just sliding that up. So if, let's say we have a sequence of random digits.
Let's do
Okay. We can assign these to our outcomes, heads or tails. So according to this, 3 is assigned to heads, 1 is so quick check. What is our empirical probability? Okay, don't shout it out. I know some of you can see this right away. Others of you maybe have some trouble, so don't shout it out. We'll give everybody a chance to figure out what is the empirical probability of seeing heads according to our trial after 15 simulations of coin flip. So just pencil down an answer or think of something. You can leave it in fraction form or you can put it into decimal form. Alright. Is anyone completely lost as to finding the empirical probability? Okay, alright. Well, if no one's lost, then what is our answer here?
0.
10 over
That's
15.
0.
It's not 0?
It's 10 out of 15.
I thought it was a simulation.
Yeah, so we simulated 15 coin flips. And how many times did we observe heads?
10.
We observed heads 10 times. So my empirical probability after 15 coin flips is 10 out of 15 or 0.6667. Okay. All right. Yes.
So you count all the coin flips together and then you count how many heads there are?
So yeah. So how many coin flips did I simulate? I simulated 15 coin
And then
flips.
you count how many heads?
Yeah. How many times did heads appear in my simulation? Heads appeared 10 times. So my empirical probability is 10 out of 15. Okay. And so, so again, this is a very simple simulation, but using the same concept, we can simulate more complicated things and get empirical probabilities that way. Okay. Don't worry. All right. Okay. So now we're going to learn. So that's it for empirical and simulations and things like that. You'll have some questions in your book. Okay, the rest of this class is all going to be spent on learning the rules for finding theoretic probabilities. And this is everybody's favorite or least favorite chapter. Okay, but we'll get through it. Okay, it'll be all right. I should put that up there. Okay, so if we have something like a coin flip, rolling a die, picking a card, we might have something called simple outcomes. Simple outcomes means every outcome has equal probability. So that's something like flip a coin, heads and tails have equal probability. Roll a die, each face has equal probability. Or select a random card. Okay. Each card you select has an equal probability. Then we might define an event, which is no longer simple. Okay, so we might have an event. An event might include many of these simple outcomes. So an event could be something like, what's the probability of drawing a face card? Okay, a face card is the jack, queen, or king. Those are the cards with faces on them. So, what's the probability of drawing a jack, queen, or king? In those cases, the probability of an event is equal to the number of outcomes included in the event divided by the number of possible outcomes. So, here's an example. What is the probability of a face card? Face card, jack, queen, or king. How many jack, queens, and kings are there total in a deck?
12.
There's 12 face cards total. Okay. How many cards total? 52 cards total. Okay, so the probability of a face card is equal to 12 over 52. 3 out of 13 if you simplify. I hope we are okay with dealing with fractions. All right? Alright, what is 3 out of 52 in decimal form? Or I'm sorry, 3 out of 13 in decimal form, or 12 out of 52 in decimal form. What?
0.27.
Okay, I don't want
0.2307.
12 out of 52, 0.2308.
Wait, how did you divide 13 by 3?
I did 3 divided by 13,
Oh, 3 divided.
or 12 divided by 52. Okay. Yes.
When should we stop rounding to like the decimal point?
That's a tough question. I like to say keep at least 4 decimals. Okay.
Okay.
That's what I say. Sometimes.
Yeah, I'm used to 3.
Okay, 3 is probably okay.
Oh, okay.
All right.
No, 'cause I don't want to forget.
If you feel like you're rounding too much, you know, keep an extra decimal. Okay. I'm usually mostly lenient, but sometimes, you know, some people on the quiz just round it off to like a whole number for something like the mean. Okay, that's not gonna work. Yeah.
Is there a minimum and maximum amount of decimals you want?
No. Okay. Definitely, if the decimal runs on, okay. At minimum 2 decimals, okay. But I would say 4 is probably a good number. All right. But you know, whatever. Sometimes in my videos I use 3 decimals. Sometimes I use 4. Sometimes I use 5. It's not an exact science here. Okay. It just, I guess because I've been doing this so much, I have a somewhat intuitive sense of when to stop rounding numbers, but it's not, there's nothing formal or finite about it, okay? Don't, don't stress too much, okay? If you round it off to 0.231, it's fine. If you round off to 0.23, I'd probably also say that's fine, okay? Alright, so anyway, probability of getting a face card. Alright, what is the probability of not a face card? So what is the probability not getting a face card?
So 40.
40 out of 52.
Yeah, okay. So we said 12 out of the 52 cards are face cards. So how many are not face cards? 40 of them, okay? So this is going to be 40 divided by 52. Alright, so 12 are face cards. So that means I'm going to put in parentheses 52 minus 12 equals 40 are not. Okay, what if you were not given, what if you didn't know anything about a deck of cards? Okay? You're an alien from another planet, and somebody says, blah, 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 probability of getting a face card is 0.2308. Alright? If you didn't know any, you don't even need to know what a deck of cards looks like if somebody gives you this answer. If somebody says the probability of a face card is 0.2308 or 3 out of 13, we can also say the probability of not getting a face card is equal to 1 minus the probability of getting a face card. So this also works. I can just do 1 minus that, and I would get 0.7692. So if somebody says the probability of rain tomorrow is 30%, what's the probability it's not going to rain? 70%. Exactly. Probability of something happening is this. The probability that it's not going to happen is 1 minus that probability. Okay? That is called a complement. The complement of an event is when the event does not happen. So the complement of a rainy day is not a rainy day. Okay? In California, it seems like if it's not a rainy day, it's a sunny day, but not always, right? So it's either a rainy day or it's not. Okay? The complement of a baby being born a boy would be not being a boy. Okay? Not being a boy 99% of the time means girl, but strictly speaking, complement is not that thing. Okay? So the complement of an event is not the event. So the not getting a face card is 1 minus the probability of face card. So formally, we would say the probability, all right, of and different textbooks will. So if we have some event A, whatever A is, whether it's drawing a face card, being a boy, having a rainy day, the probability of not that is going to be 1 minus the probability of A. So this is the complement rule. Okay? Sometimes textbooks will write A with a star next to it or whatever. A prime, there's AC, there's all sorts of things. Okay? Complement is spelled with an E, not with an I. Complement with an I is something nice you say. to somebody, help them feel better about themselves. Complement, with an E, comes from the idea of completing the picture, okay? What's that?
He's there for a second.
Okay. Yeah, so if we have rainy days and not rainy days, that completes all possible types of weather we can have, right? The weather tomorrow is either going to be rainy or not. And that covers every single scenario in terms of what kind of weather. Yes?
So you couldn't say like rain, if it's not gonna be rainy, it'll be cloudy?
Yeah, you can't say that, okay? Because if it's not going to be rainy, it's not going to be rainy. We don't want to. It's a very simple rule. It's either this or it's not, okay? And that's it. We're just forming a strict division. It's either this thing or it's not that thing, okay? Alright, we have and rules and or rules, okay? So sometimes we have different events going on, okay? We might have event A and we might have event B. So event A, we could say, is drawing a jack. So we're talking about picking cards from a deck. All right. So event A could be drawing a jack, and event B could be drawing the card 2, 3, or 4. So go ahead and calculate what is the probability of event A and what is the probability of event B. So this is just drawing a random card from a deck. You can put your answer in fraction form or in decimal form. All right. So what's the probability of A? 1 out of 13, or 0.0769. Okay, and probability of B? 3 out of 13, or 12 out of 52, and 0.2308. Yes?
On like a test or something, would we have to write both of them or just write the best one?
I will accept either or, okay? If you put it in fraction form, I can probably tell what you were trying to do. If you put it in decimal form and it's wrong, then I have no idea what you were doing, okay? Okay, is this so far okay? Yes?
Yeah.
Oh, okay, alright, this is simplified, I'm simplifying my fractions, okay?
Oh, okay.
So let me just write, probability of A would be, did you write 4 out of 52? Okay, and then probability of B would be 12 out of 52, okay? I'm just, finding, I'm reducing my fraction, that's all I'm doing, okay? The top and bottom are both divisible by 4, that's what I've done. Okay, so what if I ask the question, what is the probability of A or B? Okay, what does that mean in words? This means what is the probability of getting a jack, a 2, a 3, or a 4? In this scenario, the answer is 16 out of 52, or 4 out of 13, or 0.3077. This, okay, in our scenario here, probability of A or B, okay, this is the rule, is equal to the probability of A plus the probability of B. Okay. However, this rule applies only for what we call mutually exclusive events. Okay, mutually exclusive is also sometimes called disjoint. Disjoint events. Okay. So what does it mean to be mutually exclusive or disjoint? Okay. Well, we had in the example, in our example, events A and B are indeed mutually exclusive or disjoint. To be mutually exclusive means that if event A has happened, event B cannot also have happened. Or if event B has happened, event A cannot also have happened. So if I draw a card and it's a jack, it cannot at the same time be a 2, 3, or a 4. Or if I draw a card and I say it fulfills event B, we know event A cannot also have been fulfilled. Okay, is that okay? So mutually exclusive or disjoint means that if one event has happened, the other event cannot happen. Okay, and it goes both ways. So if event A has happened, B cannot, or if B has happened, A cannot. Those are mutually exclusive events. So our rule here is for mutually exclusive events. Okay, is that all right? event A is drawing a red card, and event B is drawing a heart. Are those mutually exclusive or not?
No.
They are not. If event A is drawing a spade, and event B is drawing a club, are those mutually exclusive?
Yes.
Yes, these are mutually exclusive. Okay, so if a card is a spade, it cannot at the same time be clubs. Okay. Are these examples with a deck of cards okay? Is everyone familiar enough with a deck of cards? Okay, kind of? Alright.
Poker player.
Huh?
You're a poker player.
If you're a poker player. Or, okay, if we don't like decks of cards, we can try,
I think we're fine.
we're okay? Decks of cards okay? Alright. Spend $3, go buy a deck of cards if you don't have one. Okay. There's actually, I think, a picture of a deck of cards somewhere in the book. Okay. Drawing a face card. Drawing a diamond.
No.
No.
Not mutually exclusive. Okay, because in these cases, if a card is red, it can also at the same time be a heart. Okay? If a card is a spade, it cannot at the same time be a club. And if a card is a face card, it could also be a diamond. So what do we do for situations where we say A, what's the probability of A or B if they're not mutually exclusive? Okay? Or not mutually exclusive events. Well, this is going to be equal to the probability of, okay, so the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Okay? A and B, this can be thought of as the overlap, or when A and B happens together. Okay? Yes, question? Yeah, PRA and B is not PRA plus PRB, okay? PRA plus B is probability of OR only for mutually exclusive events, okay? PRA and B, this is something entirely different. Right now, I haven't told you how to figure this out, other than us thinking about the event at this point in time, okay? We'll learn the A and B rule also in a moment, I think, which is, if I had to guess, the least favorite topic within this chapter of least favoriteness. Okay. All right, let's look at these events. What is the probability if I draw a card, random card from a deck of cards? What's the probability that the card is red?
1/52.
26 out of 52. Okay, half of the cards in the deck are red. So the probability that a card is red is 1/2. Is that okay? So I'm going to just write probability that it's red is equal to 0.5. I'm going to erase this over here. So notice I'm putting probability around the word red. Don't, in your notes, don't write red equals 0.5. You have to make sure you say probability of red is 0.5. Okay? Because red is not 0.5. It's the probability of getting red is 0.5. Alright, so there's 4 suits in the deck. Hearts, diamonds, overs, or clubs, and spades. What is the probability that we draw a heart? Okay, probability of getting a heart is 1 out of 4, or 0.25. So far, okay? What is the probability that a card is red and heart? Okay, so before we answer this, I know some of you guys already know the answer, but some of you, the way that just the word is phrased here just feels funny, okay? Just ask, how many cards have both traits? Red and heart. Okay. Well, there is a total of 13 hearts in the deck. Okay, 13 heart cards. How many of those are red? Are also red? All 13 of them. Okay. So how many cards have both traits red and heart? 13 out of 52, or 1/4. Okay. So, well, how many cards? The answer is 13. So the probability probability that a card is red is 0.5. The probability that a card is a heart is 0.25. And the probability that a card is both red and a heart is also 0.25. Okay? So if I say, what is the probability that a card is red or a heart? Our answer, okay, if we use the formula, this would be probability of red plus the probability of being heart minus probability of red and heart.
Wait.
Yes.
Before then, when we were doing the probability of A or B,
Uh-huh.
you said we could just add them.
That was, but I said that only works for mutually exclusive events.
Wow.
Okay? It's, like I said, it probably won't be your favorite chapter, okay? There's just a bunch of rules, alright? Sometimes things suck. And you just have to deal with it, okay? I'm sorry. I'm trying to make it as least sucky as possible, okay? But will this chapter be fun? Probably not, let's be real, okay? Some of you might love it, alright? So many of you probably will not. And that's okay. It's okay. Going from here to here. So our answer is 0.5. Yes. Uh-huh.
The large equation, is that for R in red and heart, or, cause I feel like you already found that out, so I'm not sure why we're doing the large equation.
This thing.
Yeah.
This, all I'm doing is I'm just, the rule, okay? The rule states that the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Is that okay? So that's the rule. And all I'm saying is that, well, we're not dealing with A and B, we're dealing with red or heart. So I'm just replacing every time I see A with the word red, every time I see B with the word heart. And we're using that, and we're going to calculate the probability that a card is red or a heart using this equation. And we get the answer to be 0.5. So this answers our question, what's the probability that a card is red or a heart? Okay? It might not make sense now, but you practice it this week, and it should make sense. And if it doesn't, post a question on Facebook, or come to my office hours. I'll be happy to try to sort things out. Yes?
So if it's mutually exclusive, you can add them, but only if it's mutually exclusive.
Only if it's mutually exclusive. If it's mutually exclusive, you can just straight up add them. If there's overlap, though, you can't add them because
Sacrifice, or you have to subtract the overlap, right?
you have to subtract the overlap. You'd be double counting the overlap. Alright, so let's do, okay. Let's see. So this is the rule. The rule is, what's happening back there? Probability of A or B is probability of A plus the probability of B minus the probability